Hey guys, Ms. Gosling here. In this video, you are going to learn about nuclear decay, and by the end of the video, you'll be able to define nuclear decay and solve nuclear decay problems. Now, I'm going to give you a little bit of a warning for this question, or for this topic in particular. You may want to have a periodic table handy. We're going to be dealing with elements. I'm going to do my best to give you their atomic numbers, but I sometimes forget. So just keep an eye out. If you need to look up the atomic number of an element, you are welcome to do so in this unit. So let's go ahead and get started by talking about what nuclear decay is and why it happens. Nuclear decay occurs when the nucleus of an unstable atom spontaneously changes its nuclear configuration, and it occurs because it increases the nucleus's stability. So what happens is we'll have a nucleus that is not fully stable in its configuration. So maybe it has more neutrons than might make it stable, or perhaps it doesn't have enough. In these situations, the atom will spontaneously get rid of whatever is making it unstable, changing its nuclear configuration, and causing it to decay. So there are a few different types of nuclear decay, and this is something you may have seen before in a chemistry class or even perhaps a middle school science class. But I do want to go through the different types of decay, so that way, for anybody who may not have seen this before, you'll have a good background in what these types of decay are. So our first type of nuclear decay is alpha decay, and in alpha decay, our mother nucleus, so the nucleus that is decaying, is going to release a helium nucleus from itself. So helium has 4 nucleons, has a molar mass of 4, so it's got 4 nucleons. 2 of them are neutrons, and 2 are protons. I know that 2 must be neutrons because I know that helium has 2 protons from this, the way that this is written. Now I do want to mention, just as we're doing this, the number down here tells me the number of protons that the element has. The number up here tells me the molar mass, or the number of neutrons plus the number of protons. And the big letters here tell me the name of the element. If you had anything up here, that could be used to tell you the charge. Anyhow, in alpha decay, whatever our parent nucleus is it's gonna release a helium nucleus and is gonna then turn into an element with 4 fewer nucleons and 2 fewer protons. So a good example of this is U-238, which decays into helium and thorium. So we can see here that the total number of nucleons, the total number of neutrons and protons is constant. We started with 238, and we ended with 4 plus 234, or 238 protons and neutrons. We can also see that the total number of protons is the same. We started with 92, and we ended up with 92 as well, just split between 2 separate nuclei. And that's a key part of these nuclear decay equations. The subscripts all need to add up to being the same on each side of the arrow, and the superscripts need to as well. So our next type of decay is beta decay. And in beta decay, the particle that is released is an electron and an electron antineutrino. You don't need to really know what the electron antineutrino is, just know that it's there to ensure that mass is conserved. And we can see here in the example, we have iodine, which is decaying into an electron, a beta particle, and xenon and our electron antineutrino. Similar to beta decay is positron decay. It's almost exactly the same, but instead of an electron getting removed from our atom, we are releasing a positron, so something with a +1 charge and a very small mass. Along with that electron, we're going to lose an electron neutrino, and you can see here when carbon decays into boron, it will release a positron and that electron neutrino. Finally, we have gamma decay, and no particle is released in gamma decay. What happens is just that the nuclear stability of the atom, so the atom's nuclear configuration is going to change, but it's not going to change the name of the atom, so it's not going to change the number of protons, and it's not going to change the number of neutrons. It's just going to release energy. So we have here nickel in a excited state, turning into nickel in a not excited state, and releasing a gamma particle. And you can see here, still our number of nucleons and our number of protons has stayed constant on both sides of our arrow. So let's go ahead and look through an example. So thorium-234, and just so you all know, the atomic number of thorium is 90. So another way to write this would be Th90-234, undergoes negative beta decay. What nuclide will be generated as a result? So we have thorium-234 and 90, and that's going to undergo negative beta decay. So that means we're going to release an electron and an electron antineutrino, and we're going to represent that with a curly V, which is the Greek letter nu, so it makes sense that we'd use it to represent a neutrino. And our mystery particle. So we know that our mystery particle must have the same nucleon number as thorium. Because we have no nucleons leaving, right? We're going from 234. So we need our subscripts to add up. So 234 plus 0 is equal to 234. And we know that the atomic number of our element must be 91, because 91 plus 1 is equal to 90. And that way, again, our subscripts line up. Our number of protons, or our total charge, is really the more accurate way to say this. Our total charge is going to stay constant. It's going to be conserved. So now you're going to want to take a look at your periodic table and figure out what element has atomic number 91. So when I look at my periodic table, I can see that here is our element with the number 91, Pa, otherwise known as protactinium. So here is the answer to this question. Let's go ahead and try another similar example. So this time, our thorium-234 or thorium-234-90 is going to undergo alpha decay. Let's figure out what the daughter nucleus will be, or what really the daughter nuclei, right? Because we also have our helium nucleus. So we're going to start out with thorium-234, and that is going to turn into, via alpha decay, we know that we're going to lose a helium-4 nucleus, plus whatever our mystery element is. So we know that the nucleon number for our mystery element must be 234 minus 4, or 230, so that we keep the number of nucleons constant on both sides of the table. And then we know that the charge on this new daughter nucleus must be 90 minus 2, or 88, because again, we need to keep our charge constant. Pulling up my periodic table, I can see that the element with atomic number 88 is right here. I believe that is radon. Let me go ahead and double check that for you so I'm not giving you false information. So that is actually radium, not radon. So we are going to decay. So thorium is going to decay into a helium-4 nucleus and radium. Let's do a couple more examples so you guys can see this process again. But again, I just want to remind you that our numbers on the top add up to one another, and that our numbers at the bottom stay equal to one another. Okay, so another example. Strontium-90, looking at my periodic table, I can find strontium, and that is right here, Sr, atomic number 38. And so strontium is going to decay into an isotope of yttrium, which is atomic number 39, right next to it. And we want to write down the nuclear equation for this decay. So we know we're going to start with strontium 90, so 9038 SR, and that's going to decay into yttrium, which has atomic number 39. Now, the only kind of decay that is going to give me that is going to change my charge by 1 is beta decay. So this is either positive or negative beta decay. And I know this must be negative beta decay because 39 minus 1 is equal to 38. If this had decayed into rubidium, number 37 instead, then we would know that it was positive beta decay. So we're going to go so that means that yttrium the isotope must be yttrium 90, and we also are going to need an electron antineutrino. Now, I do want to mention one other way that I could write this equation is SR 9038 turns into 90Y39 plus beta negative plus my electron antineutrino. This beta negative tells me is the same thing as saying the same thing as saying negative electron decay. So let's go forward to one last example. When iron 55, so here is our, so we have iron, Fe, number 26. When it captures an electron, it changes into manganese, number 25. Write a nuclear equation summarizing this relationship. So we're going to start with iron 55, and iron has an atomic number of 26. That iron is going to turn into manganese, which has an atomic number of 25. And we know then that this must be positron decay, positive beta decay. So we're going to have a positron that's going to enter that manganese, or that's going to be released with a charge of, or with an atomic mass of 0. So the atomic mass of manganese is going to still be 55, and we're going to, of course, have an electron neutrino as released as well to maintain conservation of momentum. And again, we can see here our superscripts all add up to 55, and our subscripts add up to 26. So with that, let's go ahead and talk takeaways. First of all, unstable nuclei undergo radioactive decay, and the 4 key kinds of radioactive decay are alpha decay, positive beta decay, negative beta decay, and gamma decay. So with that, it is now your turn to try some of these problems. Best of luck, and happy solving.